Here's what they're talking about with the squeeze theorem, just kind of in general, give you an idea, and then we'll go through the problem. If we've got some a value here, don't care what it is on the x-axis, it's ultimately that number right there, so we'll be a little interested in this problem about x being 0, but it doesn't matter, it's just some x value being a. If I've got a function, let's just call it f of x. So we erase this. Let's go f of x, a being that function there. So that's f of x. Understanding the idea of limits at a. Okay, so basically what we're doing is we're trying to find out the limit is going to tell us what that y value right there is. So as I approach from the left-hand side towards a, what is the y value going to? And then it should be matched up when I move from the right-hand side. What the squeeze theorem does is it says, okay, we got another function, g of x. And on this interval, f of x is going to be greater than g of x. So I'm just going to draw some function g of x. Maybe it looks like that. Okay, so there's g of x. And again, if we look at this, as we move from the left, approaching that a, we get to L. And then from the right, we should also get to L. But what that graphically means to us is that g of x is always below f of x. Okay, so the limit of g of x, as x approaches that a value, is going to be below the limit for f of x as x approaches that a value. Okay. But at a, both of those are L. Okay. So what we want to do here, we've got the idea. I'm just going to rewrite this down. Limit as x approaches a of g of x ends up being L, and the limit of x approaches a of f of x is also going to be L. Okay, because when we get to a, they both have that same y value. But we also remember, I mean, this is going to be critical for what we're doing with the squeeze theorem. What the squeeze theorem says is that there should be a third function. Well, there is a third function. Put it in green here. That is between these two functions. It's getting squeezed down. Okay, and does whatever it wants to do. But let's call that h of x. Okay. Well, at a, all three of these functions have a limit of L. Okay. But if we look at them graphically, the concept is that the limit of g of x, keep doing that, the limit of g of x as x approaches a is less than, okay, the limit, in blue again, the limit of f of x as x approaches a. Okay. But now the squeeze theorem, we throw that third function, and the third function is this green one. So the limit as x approaches a of h of x. Okay. And if you think about this graphically, everywhere I choose some a value, okay, let's say that my a value is right there. Okay, this inequality shouldn't be maintained. The limit of the red one, so that y value is less than the y value there on the green curve, which is less than the y value there on the blue curve at that sum a. So that's maintained. The squeeze theorem really helps for though is when these points all come together at L. So here's the idea. We want to use that squeeze theorem with this problem that we started with. Okay, so let me clean this up a little bit. I'll show you what the picture looks like here momentarily of these things. But let me do this. Okay. So what's kind of a problem here is that we have to find these three functions they call f, g, and h from this thing right here. Okay, and what's useful here is what we noticed about this portion of the function. Okay, sine of pi over x. And this is going to be basically with these types of problems. I'm assuming you're probably getting a lot of these that have a trigonometric component to them. And we know that substituting this x directly is going to give me an indeterminate value here. So we know we can't do that. That's why we have to use this alternative technique. But we should know that the sine function with the argument of pi over x is always going to oscillate between -1 and positive. So right now, we should have this idea here, -1, positive. Okay, so that function right there has that range. Okay, but now if I alter it a little bit, let's think about how I can do this. So I want to create this middle function here. I want this middle function to be this thing here. Okay, the function that I have inside my limit up top. So what I'm going to do is I'm going to multiply the middle part here by x cubed plus x squared underneath that root. Well, then if I do that, I did that to the middle part, I got to do that to both parts. So now I have this -1 over here, so x cubed plus x squared. And then I'll come over here and multiply by the root of x cubed plus x squared. And this is really the hard part about these types of problems, is determining this function here and that function there. But you got to start in the middle to do that with that sine of pi over x. The next thing then, I'm going to rewrite this as negative root x cubed plus x squared less than or equal to x cubed plus x squared, and that root times sine pi over x. It's less than or equal to then positive x cubed plus x squared under that root. Okay, so graphically, that's what those things are going to look like. This graph here is below always on this interval of this middle graph. Okay, so this graph here is below the middle graph, which is below then that graph. Okay, so the idea then is that the limit of this one as x approaches a is going to be less than the limit of this one as x approaches a, which is the less than the limit of this one as x approaches a. Okay, but our a now, instead of being just a, is 0. So what becomes nice is when this is 0, 0, and 0, in this portion here, we still cannot substitute directly to get 0 back because of this, again, this argument right there, having that x in the denominator. But over here on this function that they're generically calling maybe f in the problem, I can do that direct substitution now because I don't have any division of 0. When I directly substitute that, you get 0 cubed plus 0 squared is 0, square root of 0 is 0, the opposite of that is 0. So this gives me 0 is less than or equal to, okay, whatever this limit is. I can't evaluate this one. X cubed plus x squared sine of pi over x. Can't evaluate that one. But I can evaluate this one. Plug that 0 in, I get square root of 0 plus 0, which is square root of 0, which is just 0. So I get 0. Well, now we see that this limit here is between or equal to 0 is less than or equal to that limit is less than or equal to that 0 over here. So that means kind of intuitively that we have to have the limit of this thing has to be 0. So we've shown that that is the limit. And it's the idea, again, if we go back to that picture, okay, if that's f, if, that's g, then whatever function's in the middle here, okay, at that a term, okay, all three of those limits are the same. So if I find the limit of that one being 0, and the limit of this one being 0, then that limit has to be 0. Okay, showing you these functions kind of graphically. I think I've already typed them in yet. So this would have been, okay, this first function here is the left-hand side, the smallest limit. We see that one. Okay, and we see on that interval that that one is always below this one. So we get the relationship that our f of x, okay, which is this
this function here on the left, is always below, so the red one is always below the purple one, which would be this function right here. Okay, so we're getting that. The squeeze theorem says then that the new function, the h of x, the one that we're actually interested in for the problem, should exist in between those. Okay, and we see at this point here, it's probably going to converge. So if I show h of x, we do see that as we move along this green curve, we're going to get down to 0 at that limit. Now, it's a lot. You can kind of see the idea of calculus here, zooming in, zooming in. It's always going to continue to oscillate there. But the idea is that I can use the squeeze theorem, understanding that purple and red curve a little bit better than maybe understanding that green curve. That green curve is kind of hard to deal with, but I can deal with those two and get that idea of that limit a lot easier using that squeeze theorem. Hopefully that helps. Again, don't hesitate to ask more questions, but see if that helps. Let me know. Talk to you later.